So the structure of the genetic algorithm looks like this. Okay, so this is kind of pseudocode, and you just want to watch the basic structure of this genetic algorithm. For example, if we have a class of genetic algorithm, there should be a certain method performing evolution. So we want to grow, we want to evolve our population from the initial set to the other population having a optimal solutions, right? So we want to perform evolutions. And population is created with the initialization, and we have for loop going on. And in the for loop, we have number of iterations, number of iterative evolutions over time. And this sets how many evolutions will happen. And the offsprings are sons and daughters of this initial set. And offspring will be produced by selecting two parents. We select two parents, and what we are going to do is that we are going to do crossover a genotypes of the parents and create one offspring, right? And in that time, in this crossover, there are some kind of mutation in the genotype, and eventually what we are going to have is this kind of offsprings. And after having these offsprings, we want to substitute some of the population with the sons and daughters so that we have the next set of the population. And after doing these evolutions, what we want to find out is the most fittest ones. We want to find the most fittest best solution from this population, and we just return this most fittest one as a result of our algorithm. So you just produce the initial population generation, produce initial populations, and after that I'm gonna erase it a little bit. And then after that you just select two methods, two solutions, two genotypes to produce the next solution set, derived solution set. You just select two and create a new solution with the two selections. And after introduce some changes in the new solutions, and then place the solutions to the population. Okay. So that's what we are going to do. That's the initial, the basic structure of the genetic algorithm. What we are going to do in this week is that we are going to go through this initial population generation and the selection process and crossover process and mutation process with the problem of the traveling salesman. So because of that, we are going to take this traveling salesman problem in as an example. This is a kind of one of the simplest way to show our problem, right? There is one way to travel to like this, or the other way to travel like this, and the other way to travel is like this, and so forth. What you want to do with this Seoul, Gwangju, and Daejeon, we want to actually encode this Seoul to a certain value, like 1, and Gwangju to certain value like 2, and Daejeon certain value like 3. So we want to encode this real world series to the numbers. So that's being called encoding. So encoding step, and how to represent a solution, a genotype. How to represent genotype with a vector of genes. So that's our question. So for example, traveling 3 cities is total 3 factorial cases. So Gwangju, Daejeon, right? 3, 2, 1. There are 6 ways of travel. and 3 possible encoding strategies. So for example, we can just have the k-array coding. For example, we might just assign Seoul as 0 and Gwangju as 1 and Daejeon as 2. That is being called k-array encoding scheme. Okay. And for the convenience of the future operation, sometimes what we do is that we can do the binary coding. So for example, we do the 00 and 01 and 10. That's in binary values. It's not a decimal values. These are binary values. These are equal to 0. Actually, these are equal to 1. And this is equal to 2. If we use binary values, not these decimal values. And then what you can do is that we can just make this genotype out of this. So for example, adaptation to the problem at hand like this, position-based coding. 0, Seoul, 1 is Gwangju, and 2 is Daejeon. And 1 to 0 is that from Gwangju to Daejeon to Seoul, if we are going to travel this route, then we are going to write down 1 to 0, and it's going to be like this genotype. Okay. So that's how we can represent one trip schedule with the numbers and sequence numbers. Okay. So k-array coding looks like this. It's one of the convenient representations. K-array coding is that 0, 1, 2, this 3 array coding. 0, 1, 1, 0 is the binary coding, right? So k-array encoding means that k is the number of different genes, one of the easiest encoding way. Binary encoding is that turning the k-array numbers into the binary numbers. One of the good things is that why we turn the k-array to the binary is that actually it makes much easier in the crossover steps and mutation steps in the future. We can just flip 0 to 1 and 1 to 0. So easier for the future steps. That's why we sometimes utilize the binary values, not the k-array values. Of course, to do that, sometimes we perform the crossover on the arbitrarily chosen location. For example, if we are going to crossover around here, then actually what we are doing is that we are splitting up two values, one value in the middle. So this one is split up here and here, right? So means that sometimes unnatural choice of this performance in the future. So there are pros and cons for this binary encoding. Anyway, we have k-array encoding and binary encoding for this scheme. Okay, that was the k-array encoding. So to remember, if it is 1, 2, 0, means that 1 stands for Gwangju, right? And 2 stands for Daejeon, and 0 stands for Seoul. So it's Gwangju to Daejeon, Daejeon to Seoul, this way. So that is being called k-array encoding scheme. And there is a little bit of a different encoding scheme called position-based encoding. So position-based encoding, we still assign values to cities. 0 is Seoul, 1 is Gwangju, and 2 is Daejeon. And we have 1 to 0, and in k-array encoding is Gwangju to Daejeon, Daejeon to Seoul. There is that meaning. However, with the same values here, the position-based encoding has a little bit of different meanings. So I'm going to write down 1, 2, 0, and that is the zero's position, that is the first position, and that is second position. And in the position-based encoding, meaning of this 1, 2, 0 sequence is that here the city to visit next, the city to visit next is to visiting the city of I. Means that city 1 is the next city to visit after city 0, and city 2 is the next city to visit after city 1. So city 0 is the next city to visit city 0. City 2. So where these numbers coming from is that city 1 is the next city to visit after visiting city 0, like this, and city 2 is actually the next city to visit after visiting city 1, and city 0 is the next city to visit after visiting city 2. So if we just assemble this information, it's going to be from 0 to 1, right? From 1 to 2, right? And from 2 to 0. So it's going to be 0 to 1, 1 to 2, like this. So even though we have the same value 1 to 0, in the position-based encoding, what we are going to do is just from Seoul to Gwangju and Gwangju to Daejeon. So it's really different, right? Different travel with the same values here 1 to 0, 1 to 0. By changing the encoding scheme, we can have a different meanings. Then why we what on earth why we use this position-based encoding, which is a little bit more difficult than the k-array encoding? Can you think about why? The reason is that we want to eliminate this case. For example, in k-array encoding, 0, 1, 2, 1 to 0, and 2, 0, 1 actually represents the same trip plans, right? So if we just make this as a circle plan, 0, 1, 2, 0, 1, 2, and 1, 2, and circle plan like this, 0, 1, 2, and 1, 2, 0, and 2, 0, 1 are all the same values. However, in the position-based encoding, 0, 1, 2, 1, 2, 0, and 2, 0, 1 are all different plan. So it means that if we search through these three cases in our population, we are just kind of giving up the two chances of the search with these three genotypes, because that eventually these three genotypes represent one genotype. However, if we utilize the position-based encoding, these three values are all different plans. So we can minimize the overlapping cases. So no more wasted representation. And it's very easy to find out what are the invalid solutions are. So for example, is 0, 1, 2 valid? Actually, it's really invalid solution, because this means that 0, 1, 2 as the zeros position, and the first position and the second position means that from 0 to 0, 1 to 1, and 2, and 2 to 2, right? Like this. So then there is no trouble at all, right? Seoul to Seoul, Gwangju to Gwangju, and Daejeon to Daejeon. That's the foolish trip plan. In that case, we can write at at the moment we can find out what are the invalid solutions are, because that if it looks like this plan, then it's an invalid solutions, right? So position-based encoding gives us this kind of easiness to find out what are the invalid solutions are, and we don't want to waste our representations, and we want to have a unique phenotype for each our genotype. And in this case, we have different genotypes but have the same phenotype. Here, we have different genotypes and different phenotypes. So we sometimes utilize this position-based encoding here. So up to this point, what we have been doing is that I try to explain what is the genetic algorithm, what the genetic algorithm is, and I just introduced one difficult problem that can be very applicable to the genetic algorithm, which is being called traveling salesman problem, and how to represent that traveling salesman problem within numbers so that can be the input to the genetic algorithm, the encoding scheme. That's what I have covered so far. So in the next part of this week, what we are going to do is that actually implementing this genetic algorithm. So that's going to come in the next part. And okay, so I'm gonna see you in the next part, and have a good day.